In this section, we want to talk about exponential growth and decay models. We're also going to talk about Newton's law of cooling and heating, and then logistic growth and decay models. So if you remember way back in the day talking about exponential growth as it related to investment, you would have had continuous compounding, which would have looked like this. It would have looked like that. It would look like this, that A is equal to P times e to the RT, where the amount that you invest times e raised to the r times t is going to give you the final amount. Now, we kind of changed this up and we said, well, it's not always about money, so we're not always going to use P because that's really relegated for talking about principal. And then we said, how about this? Y equals y naught, y sub 0, times e to the kt. So up here, P is your principal. That's your beginning amount. That's what you invest. Like you invest it, you don't touch it. And in this expression, why not, or anytime you see that subscript of 0, that means some initial condition or initial value. So that why not means the initial value, whether it's the starting population, the starting mass, whatever it is. Now, when we look at this section, we see it written in a lot of different ways, but it still kind of comes down to what you have right here. So they might write it like this in a function notation, say a of t equals a naught e to the k times t. And again, just like we had the p up here, the y sub 0, y naught, we have the a naught, we have the initial value. You see in all these we have the Euler's constant e, because that's what's tying all of this stuff together. Now, do pay attention to the time, which is measured by t. Sometimes it is in minutes, sometimes hours, sometimes years. So we want to make sure that you read the problem very carefully so you know what your units are, especially if they switch from minutes to hours or hours to days or whatever. Make the appropriate adjustment for that. One of the other things to keep in mind here is that for your rate, whether it's represented by R or K, if K is positive, then we're talking about growth, positive rate of growth, right? Versus if the K value is negative, which means we have some kind of decay. And these are examples that we see all the time in the real world, and that's what we're going to look at here. Right, so the first example that we have is talking about the mass of a culture of bacteria. And it says that the mass is given by N of t is equal to 220 e to the 0.052 t. And so we can kind of see how this is matching up with the forms that we saw up above. Okay, so this 220 means your initial value. And you can call it here n naught because we're using n for the name of the function, right? And then this piece relates to our k, which is, of course, our rate. And the t, the problem here says that t is being measured in days. So t is measured in days. All right, so if we look at the questions here that are posed, so if you have your guided notes, you can follow along here. The first part here says, what is the initial mass of the culture? Well, we see how it's set up, that the initial mass is going to be 220 grams. Okay, and for uninhibited growth, we're talking about how this bacterial culture is going to grow, we would say, without limits. Now, we know in the real world, you'd be limited in terms of space and food supply. But we're talking about uninhibited growth right now. So over a short amount of time, we can definitely look at it like that. The second part of this problem is asking what is the rate of growth? Well, we see the rate there, which is 0.052. So translating that into a percent means 5.2% is your rate of growth. All right, the next part here asks us to use a graphing calculator, which we got right there, to graph the function. And we also want to figure out what is an appropriate window size here. Now, if I'm looking at this, my initial value is going to be the 220 grams. So I know that my window needs to at least in terms of the output, in terms of the y, it has to be at least 220. So we might say that our y min is 200, just so it shows up a little bit more nicely there. And then for our y max, and this is where sometimes you just have to kind of play around with it, but let's say 800 or maybe 1,000, right? And then for the y scale, I think it looks like this. Let's say we're going from 200 to 800, so you might want to make it every 50, just make it look nice. And then for your x, well, the minimum we want is 0 because that's going to be the initial value. And our max value, so if we look here, it's asking about doubling time, what's the mass of the culture in 6 days. So let's go ahead and put this at 20. Let's just see what happens with that. And then for the x scale, we'll leave this as 1. So let's go to the calculator and see what that looks like. So for my function value, no, so remember, that's what your y is, right? N of t, your function, that's your y. So I just need to type in 220, second natural log to bring up the e, so 0.052. Now I'm using x because that's the default variable when you're in this mode, and that is totally fine. Let's go to the window. So we want to go from 0 to 20. Scale of 1 is good. The y min, let's go from 200. Let's go up to 800 with a scale of 50. Let's see what the graph looks like. Yeah, so we started at 220. And it may be kind of hard to see that it is exponential. It almost looks like it's a straight line, but you can tell there's a bit of a curve as it's going up there. Okay. So we've got the graph. The question here says, what will be the mass of the culture in 6 days? So for part D, oops, I don't know what that was. So for part D, it's asking what is the mass in 6 days. Now, there are a couple of ways that we can do this. So I'm not sure how familiar you are with the graphing calculator. You could go to second graph and bring up the table and look to where it says 6. And so the mass here is going to be about 301, I guess we should say approximately 301 grams. Okay. So in 6 days, it's increased quite a bit. Another thing that you can do is that you can go back to the graphing window and I think we can just type in 6. Nope. That was wrong. Oh, if you do trace and you type in 6, it'll take you straight to where you want to be. And it puts you right there. If you want to find another value, say, what is it in 14 days? It automatically goes there. That way you don't actually have to use the trace button going left and right, because if you do that, you won't be able to land exactly on 14. See, it's kind of on the other side of that. But if I want 14, you type it in, and there you go. Now, the next part is asking, when will the culture be 300 grams? Well, you know what? I guess this is a very poorly written problem because I didn't realize it was going to be like that. I should have planned a little bit better. But you know what? Let's change this question here. Let's change it to be, when will the mass of the culture be, say, 400 grams? So when will the function equal 400? Okay, so one of the things that we can do here, we can look at the table and get an idea about when is it going to equal 400. Well, I know it's going to be after 10. We could also use trace to figure that out. Or we can do second trace to bring up the calculate menu. And option 5 would be for intersect. Well, in order to do that, we need to have another graph here. So let's plot We said 400. Let's play around with this. So there's 400. So we can see that's going to be somewhere right about here. But let's let the calculator do the dirty work for us. So press 5 for intersect. Now, easy thing to do here is press enter to select the first curve, press enter again to select the second curve. The guess, you can use the trace. You can move left and right to get close to that. And when I was younger, that's what I would do. I got to get so close. Doesn't really matter. If there's only one intersection point, just go ahead and hit enter again. And it tells you that it's going to happen at about 11.5 days. So n equals t, or n of t equals 400 grams when t is about 11.5 days. Now, we can do this algebraically too. That would be by setting 400 for n of t equals 220 e to the 0.052 t. And as we've seen with solving equations where you have a variable in the power, we're going to have to take logs of both sides. But before I do that, I have to get rid of whatever's in front of that e, because I don't want to take the natural log with that there. It just makes things confusing and gross. So those reduce. Now, typically I don't spend a lot of time reducing with the stuff on the left, but something nice and easy like reducing by a factor of 10, I'm going to do that. You might say, well, 40 and 22 have a common factor of 2. True, but I'm not all that concerned with it, and also don't want to make a careless mistake whenever I simplify, because that does happen, even to me. All right, so now let's take the natural log of both sides. So I have the natural log of the quotient, 40 over 22, equals, and again, since we're using e for the base here, taking the natural log is super helpful because that reduces away, leaving us with just that power. And we're trying to get t by itself, so divide by 0.052, 0.052. So t is equal to the natural log of 40 over 22, all of that over 0.052. So that is the exact value. Now if we go to the calculator, so let's go second quit to get back to our calculating screen. Natural log of 40 divided by 22, all of that divided by 0.052. And yeah, there we go. That's the same value that we had before. This is about 11.5 days, because again, t is being measured in days. Now the last part of this problem is asking for the time it takes to double. Now I'm going to give you a little shortcut here. Here is the shortcut. Think of this like a formula. So the time it takes to double is going to be based off of this. So for doubling time, natural log of 2 equals k times t. So you can use this when you're trying to find the rate, if you know how long it takes to double, or if you know the rate, it tells you the time it takes to double. And likewise, this could be used for finding the half-life of something. Now, the half-life is when you're talking about decay. How long does it take for a substance to lose half of what it started with? You could use this as a formula. If it asks for how long does it take to triple, well, you just turn the 2 into a 3. It's still going to work out to be the same. So for this problem, the natural log of 2 is equal to 0.052, because that's the k value from the original formula, times t. So t is the quotient of the natural log of 2 and 0.052. So the calculator will tell me natural log of 2, close parentheses, divided by 0.052. All right, so it tells me that this is about 13.33, 33 days. So we're saying that in 13.33 days, the size of the culture will have doubled in mass. So the initial value was 220, and we're saying that, well, let's use the algebra here. Well, I'm having a hard time with this. So we're saying that in 13.33 days, this should be approximately equal to twice what you started with, which would be 440. All right, so let's check that out. Now, from what we saw in the past, we saw that it takes us 11 and a half days to go to 400. So to go to 450 would take more than 11 and a half days. So 13.33 sounds appropriate. So let's check with the calculator. Let me go back to the graph. I'll do trace again. And let me type in 13.33. And it's really, really close to 440. So yeah, I feel really good about that. So it's going to take us 13.33 days to double in size. It would take us another 13.33 days to then double again and be at 880 grams. All right, cool beans. All right, so let's take a quick little break and let's see what we can do on the next problem.